In our first tutorial titled Internetworking, I will define the concepts of a computer network, internetworking, collision and broadcast domains, and the OSI reference model. A computer network is the connection of communicating devices such as wireless access points, routers, switches, PCs, mobile devices, printers, to enable the sharing of information or data. The interconnection of two separate networks using a router creates what is known as an internetwork. A network can be divided into segments of varying sizes. These segments are subject or susceptible to broadcast or collisions, which can negatively affect the quality of the network services or the available bandwidth. A network collision occurs when two devices attempt to transmit data on a shared circuit. The data collides and creates an unmeaningful data. This reduces network efficiency. In a shared circuit where multiple devices are listening, only a single device should transmit data at a single point in time, which requires the rest of the devices to be listening to the transmission. Broadcasting is when one transmitted data packet is received by all network devices. Sending one data packet to multiple recipients at the same time can lead to congestion on the network because the entire bandwidth is used to transmit that single broadcast. The more devices that send broadcast into a network, the less bandwidth is available for legitimate or beneficial use. To minimize the negative effects of collisions or broadcasts, we perform network segmentation by creating multiple collision and broadcast domains. A domain limits the effect of a negative event to a particular network segment. You can have multiple collision domains within a single broadcast domain. In the past, a network would consist of hubs, bridges, switches, and routers. A hub, which is rarely used today, was used to increase the sizes of a collision or broadcast domain. Thus, a hub is not designed to improve the quality of your local area network. In this simple topology, the hub simply increases the size of the broadcast and collision domain. Thus, the problem we are trying to minimize cannot be done using a hub. In this example, we have one collision domain and one broadcast domain. Network devices designed to improve the quality of your LAN by reducing collision domains include a bridge and a switch. A collision domain limits the effects of a collision event to a particular network segment. A bridge performs a similar function to a switch but has fewer ports than a switch. The switch is usually found on modern networks. A switch is a device capable of breaking up a collision domain, or better still, reducing the size of a collision domain. Each port on a switch is a separate collision domain. So if you have 24 ports on your switch, you can have up to 24 separate collision domains. In this topology, the hub simply extends the collision domain from the switch. The switch port to which the hub is connected and the users Bob and Paul are all within a separate collision domain from the collision domain to which Eugene is connected to. Hence, we have two collision domains because the segments are on two different switch ports. Each switch port forms a separate collision domain. Since switches by default do not segment broadcast domains, we still have one large broadcast domain which can lead to bandwidth challenges. The router is the only device designed to improve the quality of your LAN by reducing broadcast domains. So, a broadcast domain limits the effects of a broadcast event to a particular network segment. In this topology, we have 6 collision domains and 2 broadcast domains. This is a more efficient design than the previous ones. As we go through this course, you would learn how to build even more efficient networks. When networks first came into being, computers could typically communicate only with computers from the same manufacturer. The Open Systems Interconnection or OSI reference model was created to break this barrier. Consisting of 7 layers, it addresses all the processes required for effective communication. It divides the network communication process into simpler and smaller components, facilitating component development, design, and troubleshooting. It allows multiple vendor development through the standardization of network components. It encourages industry standardization by clearly defining what functions occur at each layer of the model. It allows various types of network hardware and software to communicate. It prevents changes in one layer from affecting other layers, improving and speeding up development. The application layer is the interface between your program running on your PC and the lower OSI layer. It enables you reach the corresponding program on another PC or computing device. The application layer also identifies and confirms the communications partner's availability and verifying the required resources to permit the specified type of communication to take place. The presentation layer determines how information is presented to the application layer or how information is presented to the lower layers. So it performs data translation and code formatting. A good example of this is encryption and decryption of data for secure transmission. The presentation layer therefore guarantees that data transferred from one application layer of one system can be read by the application layer of another system. When two devices or computers or even servers need to speak with one another, a session needs to be created, and this is done at the session layer. Functions at this layer involve setup, coordination, and termination between the applications at each end of the session. The transport layer deals with coordination of the data transfer between end systems and hosts. The protocols at this layer provide end-to-end data transport services and can establish a logical connection between the sending host and destination host on an inter-network. The best known protocol at the transport layer is the Transmission Control Protocol, which is built on top of the Internet Protocol. The network layer or layer 3 manages device addressing. It tracks the location of devices on the network and determines the best way or the best route to move data. A router operates at this layer. The data link layer provides for the physical transmission of data and handles error notification, network topology, and flow control. The data link layer provides node-to-node data transfer, that is, transfers between two directly connected nodes. A node can be a directly connected PC, router, switch, or wireless access point, etc. Two sub-layers exist in the data link layer. We have the Media Access Control or MAC layer and the Logical Link Control layer. The Media Access Control layer or sub-layer defines how packets are placed on the media. Contention or claim for media access is on a first-come, first-served basis. Physical addressing is defined in this sub-layer. The Logical Link Control sub-layer is responsible for identifying the network layer protocols and then encapsulating them. Switches and bridges operate at the data link layer. The physical layer does two things. It sends bits and receives bits. It specifies the electrical, mechanical, and functional requirements for activating, maintaining, and deactivating a physical link between end systems. Devices like the hub operate at this layer. As data is encoded with control information at each layer of the OSI model, the data is named with a protocol data unit or PDU in short. At the transport layer, the PDU is called a segment. At the network layer, it is a packet. At the data link layer, it is called a frame. At the physical layer, it is called bits.